Okay, good afternoon, everyone. I will introduce our recent work about the smart contract routine. The title is called "Use my function should follow my check." Okay, let us first quickly go through some background knowledge. Smart contracts are simply programs running on the blockchains, and in most cases, they are providing financial services. So there are a lot of hackers focusing on the security of smart contract because once the attack is success, there are directly financial revenue. Okay, and according to a recent study, the attacks on smart contract have already cost more than $1 billion of US dollar of financial loss. And since the security of the smart contract is so important, so their developers have created a lot of static analysis-based tools to detect the potential defects in the smart contracts. And most of these tools are rule-based. A rule-based means that there are a lot of rules for different kind of vulnerability. So, but another study have found that about 18% of the real-world vulnerabilities in the smart contract are machine undetectable, which means that they cannot be effectively detected by the SST tools. And the reason is that most of the vulnerabilities are related to the business logic, and the SST tools cannot understand the business logic. So, but if we look deeper into the SST tools, we may find that each rule is a summarization of an insecure implementation. So if we change our mind, change our way of thinking, so it is possible way to collect all the secure implementation. So when there is a code need to be checked, we just check whether it is obeyed the secure implementation. If there is a difference, it may be vulnerable. So here is a motivation example. So there are two code segments. The left one is a vulnerable one. The right one is a secure implementation from OpenZeppelin libraries. So in the right one, line 10, you may see that there is a require statement, which means that if the code needs to be executed, the amount should be less or equal than the max flash loan amount. But in the left version, this statement does not exist. So on the line 15 of the left version, it may suffer from integer overflow vulnerability. And here is our solution called the ZAP scope. The ZAP scope is very simple. It only contains two parts. The first part is to find all the secure implementations, all the specifications mined from the secure implementations. We find the secure implementations from the OpenZeppelin. OpenZeppelin is a community that provides secure templates for developing something like tokens or digital currencies based on smart contracts, and they are secure enough for others to use. So and from this, we find something called ZAP facts. The facts is something like a constraints or variable boundary, but a bit different. So we call it facts. And when there is a code segment need to be detected, we just do the similar things. We find all the facts from the code given and check whether these facts are identical with the secure implementations. So for the facts, there are three kinds of facts. The first one is something like precondition informal verification, which means that before the code is executed, there are some constraints may be satisfied. So in this case, it is from the start of a function. There may be some require statements, maybe some if condition statement, and these conditions are extracted. And during a function calling, for example, in this case, there is a mint function call on line 9. Inside the function calling, there are also some requirements need to be satisfied. And after the function calling, there's something like post conditions. We extracted before, inside, and after. There are three kinds of facts. And besides, there are still some challenges. For example, we need to do alias analysis because the variable name may be different. And which is important that we need to make sure the checks after the function call is relevant to the function call. For example, in this case, the receiver.onFlashLoan. We need to make sure that the check of the return value on flash loan is related to the function called mint. Okay, so the previous slides are only one case of the fixed mining. There is an overall workflow which contains 3 parts. The first one is to extract all the if condition or if reverse statement and request statement from the function call. We call it function definition fixed mining. The second part is alias analysis, and the third one is a function call fixed mining, which is based on the call graph. And we go through all the OpenZeppelin libraries, all the OpenZeppelin implementations. We found totally about 1,400 facts. They can mainly divide into 4 categories. The first one is about the address compliance assurance problem, such as the zero address check. The second one is about access control. For example, you want to transfer tokens that belong to other users, you need to get approval. The third one is the underflow and overflow, and there are others about the time step or stake check. We categorize them into three levels. There are 277 high risk facts, about 800 medium risk, and 300 low risk. So for the checking part, so when there is a code that needs to be checked, we are doing the similar things. We just extract all the facts from the given code and just compare it whether it is similar to the facts from the secure implementation. But there is something different. For example, for the overflow and underflow problem, if you are using a higher version of Solidity compiler, such as the version over 0.800, there is a built-in security checker from the Solidity compiler. So if you are using a higher compiler version, you do not need to focus on checks. And there are other things that are similar. Maybe, for example, we call it something equivalent. For example, equivalent overflow protection, equivalent permission checks, and maybe some extra message.value checks. And then we go to evaluation. The first one is about to compare our tool, the ZP scope, with the baseline. We choose 3 baselines. The first one is the Slither, which is a very famous open source security checker for smart contract. The second is A-Checker, and third is SOMO. Both of these tools are about to focus on detecting the access control problem. They are proposed in the recent maybe 3 years. Yeah. And the last one is our tool. We evaluate these tools on a data set of 51 real-world security bugs caused by the insecure use of OpenZeppelin libraries. Our tool have found 41, and which significantly outperform other baselines. And for the because the previous tool only contains 51 cases, we also collect the top 15,000 contracts from 3 different chains, and we sample them and memory label them to do a larger scale study. Our tool have reached about 89% of accuracy on this large data set. And for the third research question, we're trying to find something new. The first, we have found 15 new vulnerabilities involved in contracts that contain more than $439. And we have found the problem that the absence of zero code checks is pervasive. Although the absence of the zero address checker may not directly cause the loss of asset or financial loss, but sometimes it may lead to phishing attacks. And the third one is maybe a champion of intentionally losing a check. In this case, on line 10, there is a mint, there a call of the mint function. So in the OpenZeppelin implementation, there should be an access control check. You cannot mint others' token. But in this case, there is no such check. But however, this code is still not vulnerable because on line 11, there is a call of transfer. In the transfer, there is an access control check. You cannot transfer others' token. So this case is still secure. Yeah. So, and besides, we also do a cross-chain also do a cross-chain comparison. We have run our tools on a very large data set across 3 chains. Maybe the BSC chain is a bit newer. There are less high-risk contracts, and in the Polygon, the high risk is significantly higher than others. Okay, that's all. Thank you. And questions?